Telescopes. So telescopes are instruments that collect and focus light and also other forms of electromagnetic radiation. So maybe we were just thinking that telescopes are the devices that working optically collecting the light rays, but it's not collecting only the visible lights, but there are telescopes that we can collect radio waves, X-rays, right, such like electromagnetic radiations. So in this class, we will be learning about the history, lenses and hardware, then the reflecting telescopes, refracting telescopes, and about observatories. So the when we talk about history of the telescopes, so the Hans Lippershey, who lives in Middelburg, Holland, he's the one who invented the refractor telescopes in 1608. But Galileo is the first one to use these telescopes in astronomy. And also he is the one who designed a combination of convex and concave lenses to use in the use of telescope. So Galileo is the one that who's famous for the inventing the telescopes. Then Kepler is the third person who improved the design to have two convex lenses, so which made the image upside down. And this Kepler's design is still the major design of refractors today. But there are a little bit few improvements in the lenses and the glasses that we are using to make them. Also, we are combining these with chips to record these spectrums and data. So we have a lot of improvement for the design that Kepler improved. Well, so why can't you see an object that is far away, right? So we are using telescopes to see the things that stay far away, right? So why can't we see the objects that are staying far away? So the answer is very simple, right? The objects that are in far away does not take up much space on our eye screen, basically at retina, right? So using a digital camera, so analogy at 150 feet, let's think about writing on a dime. Like it does not cover enough pixels on your retina, retinal sensors. So you cannot read those writing. But you can correct this error by bending the light with lenses. Remember last week not last week, this week Monday class, we learn about like what happened to the light when it travels through different mediums, right? So we can bend lights using different medium, entering the light into different mediums. So by bending the light, we can increase this collection power of light, so we can see the faraway things better. So in order to do that, we are using lenses. So the lenses in our eye works like a glass lens. So the light bends as it goes through a different medium. Remember, that I mentioned earlier. So when we have a lens, the light rays can bend and focus into a point, right? So in a concave lens, so if you are sending parallel light rays, it's collected in one point, and we call this as the focus point. Likewise, in our eye, we have the eye lens, which is concave lens, and the light beams are collecting back in the retina. So in a when we have a young eye, or the eye with no health issues, the light should collect in the retina, and we should be able to see the objects clearly. Now, as I mentioned, when the light enter into the lens, it bends like this. And when the image is created on the retina, we can see it. So here, if you are looking at a dog, then the light rays that's coming from this object, the dog, it will create an image at the back of the retina, and our brain can read that object as a dog. So how does this apply to telescope? So if you had a bigger eye, you could collect more light from the object. So this image could be magnified, so it stretches out over more pixels in your retina. So in a telescope, there are two pieces that make this possible. One is the objective lens and the other one is the eyepiece or the eye lens. So if you look at this picture, this is where we keep our eye to observe things, right? So we call this lens over here is called the eyepiece lens. So the other one on top here where we focusing towards the object or the star, let's say if you're observing a star, we are focusing this side to the star. So this is called the objective lens. The lens inside is called the objective lens. Or the primary mirror in reflectors. So we'll learn about two types of telescopes in next slides. So anyway, so if we have a refractor telescope, we call this as the objective lens. If we have reflectors, then we call this as the primary mirror. So anyway, by having that, we can collect a lot of light from a distance object, basically a star, and brings that light of image to a point of focus. So it will focus into a one point somewhere in the telescope, and then we have the eyepiece, which has another lens, and that will take the bright light from the focus of the object lens or the primary mirror and spread it out and magnify it basically to make up a large portion of the retina. So this will make the object looks bigger or brighter, right? So basically the principle is the principle of magnifying glasses. So like if you're using a magnifying glass, you can see small things bigger. So basically that is what it does in the eye lens. So again, if you look at this picture, so this is how we see things. So here's the objective lens in a telescope. So the light rays that's coming from this tree will be focusing into this point. And then we have the eyepiece that's keep in the focal length between the object image that created over here. And then it sends a lot of light rays into our eye. So we can see that tree bigger and also maybe closer. Here's another picture of the simple telescope. So the principle of simple telescope. So if you're looking at a tree somewhere and those light rays. So here's the tree should be somewhere here, upright, and the light rays comes into the objective lens, then it's collected it in the focal point. So here the image, the first image that created by the objective lens, then that light rays will enter into the eyepiece lens, and we will be seeing there will be a image on our retina which is somewhere here. So this is the final image. So the faraway object is visible somewhere closer to our eye, and also it is a relatively big size, right? So if it is far away, we cannot see a big tree, we will be seeing a small tree, right? But when we're looking at the telescope, we see this big final image, and also it is upside down. But like when you're observing the objects far away, like a star or a moon, we don't mind whether it is upside down or upright. We cannot really judge whether it is upright or other way around, inversed, right? So it doesn't matter, but in a telescope, we seeing objects that are far away, closer to us, and also it is upside down and bigger. All right, so when you combine the objective lens or the primary mirror with the eyepiece, you have a telescope. So again, the basic idea is to collect lots of light to form a bright image inside the telescope, and then use something like a magnifying glass to magnify that bright image so that it takes up a lot of space on your retina, relatively bigger space in your retina, rather than seeing a object without use a telescope. So there are two general properties of telescope. One is how well it can collect the light. So we call this, using the aperture, we can change that. And then how much it can magnify the image. So magnification, right? So objective lens property and the eye lens property. Then what we mean by the aperture. So a telescope's ability to collect light is directly related to the diameter of the lens or the mirror in the objective lens, objective mirror. So we call this as the aperture, and that is used to gather light. Generally, the larger the aperture, the more light the telescope can collect and bring to focus, and the brighter the final image. So better the aperture, we get a better picture. Then the magnification. So the telescope's magnification, its ability to enlarge an image depending on the combination of lenses used. So it is not just a property of eye lens, but the combination of both objective lens and the eye lens. So the eyepiece performs the magnification. Since any magnification can be achieved by almost any telescope by using different eyepieces, aperture is a more important feature than magnification. So the eyepiece, the purpose of the eyepiece are varying. So the one is produce and allow you to change the telescope's magnification. And it also produces a sharp image in our retina and provide comfortable eye relief, the distance between your eye and the eyepiece when the image is in focus. You know, like when you are looking at a telescope, you don't need to keep your eye like embedded into the eyepiece of the telescope. You can have a little gap in between the eye lens, your eye lens, and the telescope's eye lens. So it's make a little comfortable for the user. Then determine the telescope's field of view. So apparent view and the real view. Apparent means how your visible view, right? So how much of the sky in degrees is seen edge to edge through the eyepiece alone. So this is specified on the eyepiece. Then true or real, how much of the sky can be seen when that eyepiece is placed in the telescope. So true field is apparent field divided by the magnification. So so to see a better picture, we need to have a higher magnification. So the magnification, the telescope's magnification, its ability to enlarge an image depending on the combination of lenses used, as I mentioned earlier. So the eyepiece performed the magnification. Since any magnification can be achieved by almost any telescope by using different eyepieces, apertures. However, the aperture is the more important feature than magnification. I think I already mentioned that, but two things are really important maintaining a good telescope. Then we will be using filters depending on what we are looking at. So recently I used a telescope to observe Saturn, and in that we cannot see those colorful rings, but we saw a black and white picture. But if we use a filter, then we should be able to filter out the colors depending on what material those rings are made of. So the filters are pieces of glass or plastic that you can place in the barrel of an eyepiece to restrict the wavelength of light that come through in the image. So as I mentioned, if I'm seeing a black and white picture, because I didn't use any filters, but if I use filters, it will filter out some wavelength and give us a colorful view. So set of filters for viewing, including a light pollution filters. So the left picture on here is the light pollution filters, and the colored filters from enhancing contrast in planetary images. So filters can be used to enhance the viewing of faint sky objects in light polluted sky, and then enhance the contrast of fine features and details on the moon and planets. Then safely view the sun. So there are sun observable telescopes. So this is a picture that taken by a telescope of Neptune. So Neptune viewed without adaptive optics. So, you know, like you can modify the optics of telescopes by using filters and other stuff. So this is a picture that taken of without using adaptive optics, so Neptune. Then here we put some adaptive optics, and even we can observe these cloud bands and storms. And this is a picture that taken from the telescope that's on Earth. So see, like you can see more detail about the planet. All right, so please answer the questions below, and also we'll continue in the next video.